This is question 2 of the mock. Explain why chromium complexes are coloured, and we need a perfect answer for this. Now, I don't know whether this is going to be a perfect answer, but if it is, good. If it's not, try and improve it yourselves. All right, let's do a bit of background first. We've got chromium. This is Cr3+. Okay, and if it's just floating in space, it's known as an isolated. It's an isolated ion. All right. Now, when we put this guy, into what's called a ligand field, okay, we get this. It's in now. Oops, this hopefully. Oh, there you go. That's good. This is now in what's called an octahedral ligand field. Okay. Now these can be any ligands. All right. Water, ammonia, anything. Now the thing is, in the isolated ion case, all of the d orbitals are of the same energy. There's 5 of them, like this. Okay, so this is this situation here is this situation. They are what we call degenerate, and we should all know that. But when they're in a ligand field, they split. Okay, they split into 2 at the top and 3 at the bottom. Now, we don't have to say which ones are which, not in this question, but that's how they split. Now, for your information, the ones at the top are 3. Oh, yeah, is it 3? Yes, 3, isn't it? 3dz squared and 3d x squared minus y squared. And the ones at the bottom are 3dxy, dxz, and dzy. Okay, and there you go. You have electrons in these lower ones here, and they can jump up to there, can't they? So this is in what we call an octahedral field, or ligand field, we should say. All right, and when they're in octahedral ligand field, they split. The d orbitals split into 2. Okay, that's vital. All right, and now obviously, as you all know, let me get a nice color here. One of the electrons from the lower can be promoted to become one of the ones in the higher. And the energy gap, delta E, is equal to HF. And if the frequency absorbed, this frequency here, is in the visible, if it's in the visible, we don't see that color, obviously, but we see the complement color. Okay, so that's basically why they're coloured. Now, what can we get rid of? Well, we don't really need to talk about the isolated ion in this case. You should know that, but in this case you don't. All right, so I'm going to try and build an answer here. All right, from this stuff. But you don't need to start off with this. And we don't even have to say they're degenerate when there's no ligands around, when they're isolated. Okay, we really should start off here. Okay, because it's talking about complexes. It's not talking about isolated ions. Okay, so the first thing. Okay, this is how I would do it. Now you can improve on this if you want. Okay, in a chromium complex, the ligands split the d orbitals into 2 energy levels. Okay, that's this here. Okay, so in a chromium complex, the ligands split the d orbitals into 2 energy levels. Okay, that's the first thing I'd say. Electrons go, well, sorry, let me make it perfect if we can. Electrons absorb energy, all right, and are promoted. My spelling's not very good, is it? Promoted from a lower energy orbital to a higher energy orbital. Okay, so in a chromium complex, the ligands split the d orbitals into 2 energy levels. Electrons absorb energy and are promoted from a low energy orbital to a higher energy orbital. Okay, now there you go. All right, different color. The electrons absorb photons from radiant light. In other words, where do they get the energy from? From the light that falls on them, from the radiant light. Okay. If the energy absorbed is in the visible part of the spectrum, if the energy absorbed in the visible part of the spectrum, the complement color is seen. All right, now I don't know if you think that's a perfect answer, but let's have a look. What does it say? Oh, a nice color there. Let's go and get a red. Okay, so we need to say it's separated into two energy levels. That's important. Okay, two sets of d orbitals. We need to say electrons absorb energy. We need to say they're promoted from the lower to the higher. Okay, that's very important. We need to say, what do they absorb though? Well, they absorb parts of the radiant light. They absorb photons from the light. And we also need to say that we see the complement color. All right, so again, I don't know. You can polish this up yourself. I'm sure there's millions of mark schemes now that you can look at, but I think this is a pretty good answer. Okay, this isn't bad at all. It's mentioned everything we've got to mention. Okay, whatever you do, you've got to get a perfect answer and use it. All right, so let's stop that and do the next one. Okay, this is the second question, or part B. 4 different compounds can be obtained when anhydrous chromium 3 chloride reacts with water under various conditions. When samples of each compound are reacted separately with aqueous silver nitrate, different amounts of silver chloride are precipitated. The precipitation leaves the complex ions P, Q, R, and S in solution. Okay, there's the formula of the compound there, and moles of AlCl precipitated per mole of complex ion. There's 3 there. Complex ion is P. Property of the complex ion is nonpolar. Okay, so what we've got to do, and a lot of you missed out on this, the drawings have to be 3-dimensional. That's important. They do ask for that. And also, a lot of you missed out on this, and I was very nice when I marked it. You didn't put the charges in either. All right. So let's have a look at this then. Right, now in the first one, this is P. So P is going to precipitate out 3 moles of chloride ions. That means all of these are going to go. All 3 are going to go. So the complex ion left is just going to have water as the ligand. Now we've got to show 3-dimensionally what that looks like. Let me get a nice pen. Let me pick this dark blue. Okay, so we've got to show these wedges coming out and these dots going back in. Okay, and now we can put the water. There's one. It's the oxygen that has the lone pair. So you should draw the oxygen, which is the one bonded. There you go. Because this, what's left here, you see, it's just the water. We've sucked out all of the chlorides and we've got the water. And this is how you should show it. Now, what's the formula of this? Well, there's the formula, isn't there? But what's the charge of this? Well, it's one of these guys to 3 chloride ions. Okay, so the charge on this thing must be 3 plus. Okay, to give the neutral compound. All right, that's that one done. All right, that's worth 1. Okay, as I say, a lot of you didn't bother with the charge, and you should have done. A lot of you didn't bother with the 3-dimensionality, but you should do. Let's have a look at Q now. 2, it's polar. Oopsie daisy. 2 is polar. All right, and it sucks out 2 of the chloride ions. So there's 1 left. So this becomes a 2, and there's 5 waters. So it's polar. All right, so it's got to be polar, hasn't it? Really. So let's put these again, the 3-dimensional nature, and that goes back, and that goes back. Now the chlorine can go anywhere here. It doesn't really matter. I'm going to put it there because it's polar. There's only 1, so it's got to be polar. But now I've got to put my, now I've got to put my waters. H2O, 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 H2O. I think that's it, yeah. And now this is obviously chromium is 3 plus this guy. It's 2 plus now, isn't it? Because we put a Cl minus on it. So this guy has a 2 plus. Now this one takes out one chlorine, so this is Cl2 now. And this is polar again. Okay, so let me draw my structure. There, and there. Oh, that's not great. Okay, that goes back into the distance. Now it's polar, so that means the chlorines cannot cancel each other out. So let's put them on the plane, one there and one there. Yeah. Now the charge on this thing. Oh, let's have a nice color. Let's put my waters in first. There's one water. There's another water. Whoopsie daisy, another water, and another water. And this time it's going to be +1, isn't it? All right, because it's Cr is 3 plus 2 Cl minus ions. We're going to get an overall charge of +1. Simple as that. Now this one is polar, and I've drawn these two in a polar position. Now the next one is exactly the same charge, okay, but this one's got to be non-polar. So now there's one there, one there. We've got to draw our three-dimensional structure. Now, let me put the Cl here. It's got to be opposite, hasn't it? It's got to be exactly opposite. So the molecule, or so the ion, the complex is nonpolar. All right, now let me put my waters in. H2O, 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 and H2O. Okay, now a lot of you should have had marks knocked off, to be honest with you, because you didn't put the charges. All right, but you should. All right, now suggest why S is non-polar. It is non-polar because the polar groups, which is the Cl atoms, are opposite each other. Okay, that's good. All right, but I really want you to say this. And so the dipoles cancel out, leaving something that is non-polar. All right, now you've got to say all of this rubbish, eh? All right. Anyway, let me stop that and come back to you when I get the next bit done. Now this one shows the structure of picolinic acid, and there it is. Conjugate base is a bidentate ligand Z. So picolinic acid isn't the ligand, but the conjugate base is. Now we've got to define the term bidentate ligand. Now what are the pivotal things here? What are the things we must say? Okay, number one, it donates 2 lone pairs. That's important. 2 lone pairs to the central metal ion to form 2. Well, let me write that as words. 2 dative bonds to the metal. Okay, what did we do in the exam? Very, very many of you forgot there was 2 there. There's got to be 2 because it's bidentate. And you didn't say it forms 2 dative bonds. And you've also got to say to the central metal ion. Okay, that's very important. So draw the structure of Z. Now you should remember this. This is a bit of acid-base theory, isn't it? So if this is picolinic acid, the conjugate base is going to be this guy. Okay, there it is. Let's draw this guy to start with. That's picolinic acid. But it's going to have its hydrogen knocked off, isn't it? It's going to be like that, and there plus H plus, and there's going to be an equilibrium there. So this is the acid because it donates the proton, and this is the conjugate base. And they must differ. Acid and conjugate base only differ by a proton. So draw the structure of Z. It is this. Oops, this is this thing. So let me draw it again. A nice benzene ring. There's a nitrogen there. This is CO2 minus. Double bond there, double bond there, double bond there. Now, lots of you missed out on this very silly answer because you didn't put the double bonds in. You forgot. Okay, you've got to do those. Okay, and I know it's only 1 mark, but it's 1 mark that you'll lose, eh? All right, so Z reacts with chromium 3 ions, this guy, in a 3:1 ratio to form a neutral complex. In other words, well, you know this is bidentate. Whoops, that's not how you spell it. No, neither is that. Bidentate. So you're going to need 3 of these. Okay, and each one is going to form two dative bonds. All right, so Z reacts with aqueous chromium ions here in a 3:1 ratio to form a neutral complex. State the coordination number and the geometry of the chromium 3 in the complex. Well, the coordination number is going to be 6, okay? And the geometry is going to be octahedral. It must be if it's coordinate 6. All right, so let me knock that off and get to the next bits. Okay, some equations here. This guy, ammonium dichromate, decomposes readily on heating to form that, steam, and an inert colorless gas. Deduce the oxidation number of chromium in that and that. Well, chromium in this, it's +6. If you don't understand this, give me a shout and I'll do it for you. Chromium in this one is +3. All right, that's 1 mark. And the equation, here we go. Well, obviously the gas is going to be ammonia, isn't it? So we get NH4 twice, Cr2O7, and it decomposes, and as it said, it decomposes to this, so we get that. We're going to get the colourless gas, which is nitrogen, and we're going to get 4 waters. Now, why did we lose marks here? Because you didn't balance. It must balance. It must balance at A level. If it doesn't balance, you don't get the mark. Sorry, guys. All right, let me stop this and go. Oh, there we go. We finished this question. All right, let me stop this now.